let me say that it's my pleasure to introduce our speaker today, Bob Litterman. And I can just say a few words about him. He has a very long bio, which I'm not going to read the whole thing, but he is the chairman of the risk committee and founding partner of Kepos Capital. Prior to this involvement, he enjoyed a 23-year career at Goldman Sachs, where he served in research, risk management, investments, and thought leadership roles. He was named a partner in 1994, is author of several books, and is well known for several methods. Black Litterman has made him quite famous in the academic community as well. Bob earned I didn't know this until I read recently your bio, PhD in economics from the University of Minnesota, and a Bachelor of Science in Human Biology from Stanford University. He was inducted into the Risk Magazine's Risk Management Hall of Fame and named the 2013 Risk Manager of the Year by the Global Association of Risk Professionals. And he also, this goes on here, these different awards. I guess the CFA Institute Board and International Association of Financial Engineers, Financial Engineer of the Year Award, etc. Anyways, we're really happy to have him here to give this talk. And the talk is Pricing Carbon, a Pragmatic Approach to Address Mankind's Greatest Risk Management Problems.
Thanks, Tom, and it's a real pleasure to be here. The presentation that I brought is kind of an academic version of a paper that I've written with two co-authors, Kent Daniel and Gernot Wagner. They're very useful co-authors for me because Gernot is an expert in environmental economics and Kent is an expert in finance and behavioral finance in particular. And we've been working on this paper for, about 5 years, and we keep learning new things and finding new things. So I'm going to go through it kind of quickly, but before I do, I just want to kind of set the frame. And, my background is in risk management. So when I got ready to retire from Goldman Sachs, one of my colleagues there asked me if I'd be interested in environmental causes. And I said, well, could be, I don't know. And he kind of introduced me to some folks at various different places, including the World Wildlife Fund. I started getting involved. And I'd been interested in, like probably many people, this is about 10 years ago, in climate risk. It's something you hear about, you don't think much about. And so I started digging into it. And of course, what I realized early on was that it was a risk management problem. And I went back to my colleague, Larry Linden is his name, who got me interested in this. And I said, Larry, this is obviously a risk management problem. It's also obvious what we need to do. We need to price the risk. And he said, well, that's true. A lot of people understand that, but no one knows where to price it. And so I thought, oh, well, that sounds like an interesting problem. I could probably dig into a little bit and see what's going on there. It can't be that difficult. And here I am, 10 years later, still trying to deal with it. But one of the things that I realized is that in particular, the standard models of what's called the social cost of carbon, which is the appropriate place to price climate risk, don't adequately take risk into account. And so that's something that we've tried to do in this paper.
Can you tell us what you mean first by climate risk and second by pricing climate risk?
Sure.
Okay.
Well, we'll talk about damages, but basically, when we emit carbon dioxide or other greenhouse gases into the atmosphere, it creates a degree of warming, and that creates the potential for a wide variety of outcomes, some of which we know about, many of which we probably don't know about because it's a complex experiment that we're doing. So that's the risk component. That's what I mean by climate risk, is that uncertain distribution of damages. And then pricing it is what do you do about that? And this is a classic externality. The risk is created by burning fossil fuels primarily and other economic activities. And the problem is that we're not creating incentives to reduce those emissions. So what we need to do is figure out how big is that externality and then create the appropriate incentives to reduce that. And so basically it's well known that what you want to do is look at what's the marginal increase in the damage, the expected value of that today when you're operating at an optimal path, or let's call it the incentive to reduce emissions, and that's where you should price it. It's classic externality. So in that sense, the framework is kind of well understood, but the difficult problem is, and now many people, by the way, don't emphasize this, but the question is not what's the damage created by the next ton of emissions, so to speak, when we're not pricing emissions. The question is, if you're on an optimal path, so that I'm pricing emissions, and I will price emissions going forward based on whatever information I have. So if I learn, and of course we will learn about damages and about the demand for sustainable energy and so on. So we'll learn a lot. As we learn over time, we want to adjust the price to reflect that new information. And given what we know today, what's the appropriate price? And then at that price, and assuming that we follow an optimal path, what is the marginal increase in damage of the next ton of emissions that's created? And so if it's going to create another $100 worth of damages, I should create an incentive of $100 not to do it. So price the externality. But you can already see it's going to be a difficult problem, because I have to estimate what's going to be the long-term impacts of this ton of carbon along this path, and what are they worth today? And obviously it's an uncertain future. So the main message, or one of the main messages of the model, is designed to suggest that you have to think about the full distribution of outcomes. And so by way of sort of motivating this paper, there are lessons from financial risk management that apply to addressing climate risk. And the first one is you have to consider worst case scenarios. Now, if you think about this in the context of the public discussion of climate risk, what you might know is that if I start talking about worst case scenarios, people are going to say, oh, you're an alarmist. Well, I just say, no, I'm a risk manager. And, as a risk manager, that's your job. If you don't think about worst case scenarios, you're just not doing your job. And so that's number one. Number two is that risk management, particularly a risk that's known and is growing, is a high priority. It's an urgent issue. I tell people, when I was head of risk management at Goldman Sachs, it was never the case that I went to senior management and said, we have a risk problem. And they said, oh, okay, let's talk about it next week. It just never happened. Maybe at other firms it does, but at least at Goldman it didn't. And for obvious reasons. Or maybe it's not so obvious, but there's a concept, I would call it in risk management, called time compression. And time doesn't really compress, but sometimes it feels like it's compressing. I experienced that in August of 2007 when the quant space melted down, and I had a large quant business. And we thought we would have months to get out of positions, and we had hours, and that was a problem. So, and in fact, more generally, I would say the point is that if you have enough time, you can solve almost anything. Okay, it's when you don't have enough time, it's when you run out of time, when things start happening more quickly, that things get out of control. And in this context of climate risk, there's so much uncertainty about what's going to happen and when. We have to worry about that. And time is a scarce resource because we just don't know how much we have. And that'll become more explicit in the model. And then finally, the purpose of risk management is not to minimize risk, but it's to price risk appropriately. And again, that's probably fairly obvious. When When Goldman Sachs decided in 1994 that they needed to have a risk manager, that was the first time they had one, because prior to that, all the partners thought they managed their risk pretty well. But, we were getting big and some of the partners weren't managing their risk so well, so the other partners decided we need to have someone quantifying our risk. Now, they didn't appoint me head of risk management in order to minimize risk. That was very clear. They wanted to take risk. They were making a lot of money taking risk, but they wanted to take smart risks. They wanted to make sure that when they took a risk, they understood it and they were getting paid for it appropriately. So I would say the essence of the problem with climate risk can be viewed as we're not pricing that risk. We're not giving economic agents in the economy the incentive to minimize the amount of pollution, because there is an externality. The externality is the risk that pollution creates, this kind of pollution, and then we're not pricing it, so we're creating too much of it. Another way of thinking about it as an economist, I'm trained as an economist, is to say, look, we have a scarce resource, the atmosphere's capacity to safely absorb emissions. We don't know what it is. We don't know how much capacity there is. It's unknown, but it's finite, If we keep raising the amount of greenhouse gases in the atmosphere, it's usually measured as a parts per million of carbon dioxide, which is a bit of a simplification, but, we just crossed 400 recently. The level for a long, long time was about 280 prior to the industrial age. I was born in 1951. It was, probably still under 300 at that point, and it has just started to grow exponentially. And that is the emissions have grown exponentially. It's actually there's a stock flow issue here, because it's the amount in the atmosphere that actually creates the warming. So if we cut off emissions today, we would still be warming. Sometimes people they show a picture of a small Earth on top of a Bunsen burner that's heating it up. Okay, well, the carbon dioxide in the atmosphere is the amount of flame there. So we can turn off emissions, and that thing is still heating up the Earth. This is a serious problem. So how do we think about that? Well, we've got to bring the science and the economics together. Oops. So, but I want to motivate that a little bit by referring to Johnstown, Pennsylvania, a nice, quiet, bucolic area. They had a steel mill in Johnstown, and in 1889, they had outside of town a hunting and fishing club. And they had an old reservoir that had been converted into a lake, which they used for fishing, but they didn't do a very good job of fixing up this old dam. And in 1889, it overflowed. And when it overflowed, there was a non-linear impact because it was an earthen dam. And so the water flowing over the top eroded it. That created a larger flow. And within a couple of hours, the entire dam, which you can see was a 72-foot structure there, was gone. And all that water from this huge lake flowed down this narrow gorge and flooded Johnstown. It killed over 2,000 people. And so think of the atmosphere as this reservoir, and you can think of the level as the amount of parts per million. And the question is, at what point does it overflow? In other words, at what point is there a catastrophic outcome? There's plenty of damages before it becomes catastrophic, but at some point, it's going to become catastrophic. And we don't know, is that at 550? Is that at 600? Maybe it's at 350. Think about that probability distribution. And so whatever that is, and we're at 400 today, the amount of carbon dioxide that gets us to that first catastrophic tipping point is the capacity of the atmosphere. Okay? It's not unlimited. And you can think of it as a scarce resource. So how do we allocate scarce resources? We price them. So where should we price that resource so that we use it efficiently over time and to the highest and best use? And how much is that going to cost society? The answer is basically the social cost of carbon or at least that's the name that economists give to it, you can think of it as the answer to the simple question, how serious is climate risk? And that was kind of the question I was asking myself. And when Larry, my partner, said, no one has a clue, I thought that's not a good enough answer. We have to figure this out. So how does it work? Well, we have a very simple model, and we're trying to capture the risk. It says here, the risks and uncertainties surrounding climate change. Let me reference the difference between risk and uncertainty. I won't talk much about it, but to me, uncertainty is a much broader concept, and risk is, in the context of a model like this model, a specific set of outcomes that we can put probabilities on. Okay. What else might be in the broader concept of uncertainty? Well, my model is certainly a oversimplification. In fact, it's basically a toy model. I don't want you to take it seriously or think that I take it seriously. It's trying to get the concepts right. But we can talk about various components to it that really would have to be made much, a lot more effort would have to go into them before I would take it seriously. But hopefully it illustrates how to think about this problem. But it's misspecified. And, first of all, it may not be the right model. Even if it's the right model, it's oversimplified. So there's kind of model risk and there's misspecification risk. And one could think of lots of different models. So risk in this context is just, if we took this model and said this is true, then there's a variety of potential outcomes, and we kind of put probabilities on them. So the model incorporates a mapping from greenhouse gases this is from emissions of greenhouse gases to the level of greenhouse gases in the atmosphere, which drives the warming, forcing, sometimes it's called, which drives up temperature. It also causes acidification of the ocean, and then there's stronger storms and so on, which lead to damages. Now, it may lead to improvements as well. In northern Canada, maybe they can grow wheat where they couldn't grow it before. So there's pluses and minuses. But think of this from if you think about contingent pricing of cash flows, think of these damages as being future cash flows. So there's an uncertain distribution of future cash flows. Most of them are negative, some of them might be positive, and we want to calculate their value today. That's a very standard asset pricing problem. Now, sadly, one of the first things I realized was that in these typical models that economists use for calculating the social cost of carbon, they take all those uncertain cash flows and they discount them using a discount rate. And you often hear economists talk about how important the discount rate is, because these cash flows are going to occur in many cases hundreds of years into the future. And as you, I'm sure, are all familiar, if you discount them at 1% a year, they're going to be a lot more valuable today than if you discount them at 2% a year, if you go out 100 years. And so it's very important. So economists have thought a lot about, what's the right discount rate? Is it 2%? Is it 3%? Is it 4%? Actually, just about a week ago, one of the economists who's the leading expert in this field, Michael Greenstone, University of Chicago, very smart guy, testified before Congress. And, Michael knows better, but in a lay audience, he sort of talked about different discount rates, why they're important, and what might affect their level. And one of the things he mentioned is, kind of risk. Well, in an audience with financial engineers and who work on derivatives pricing, I would guess you're all very familiar with the fact that you have to think about the marginal utility in different states of nature. And so we'll talk about that. And as you may also be very familiar, or maybe not so familiar, economists have discovered that you need a more flexible utility function, something called Epstein-Zinn as an example, in order to discount cash flows that occur very far into the future and that have different, significantly different marginal utilities in different states of nature. In other words, there's good states and bad states, and this was first focused on in the context of equity payouts. So equities tend to pay out a lot in good states of nature when the economy is doing well, and they tend not to pay out so well in bad states of nature. So turns out equities, because they have that property, they pay out when marginal utility is low, they're not as valuable. Things that pay out when marginal utility is high are more valuable. So being short equities, for instance, would be an example of something that pays off when marginal utility is high. And because it is such an insurance policy, if you will, it requires a lower rate of return than being long equities. In fact, a negative rate of return, or at least below the risk-free rate. So, and then finally, this last caveat, which I kind of already referred to, think of this as a toy model. It's not a serious model. Okay, so this kind of shows, first of all, the sort of flow here from greenhouse gas emissions and a degree of mitigation. So we're gonna allow mitigation, which costs some money today, and we're going to mitigate a random variable x, t, percentage of the emissions. So you can think of that as going from 0 to 1, but we actually allow it to be greater than 1, meaning that at least in theory, you could suck greenhouse gases out of the atmosphere. There are technologies for that today. They're very expensive. It's estimated that at something like $500 to $1,000 a ton today, you could suck out carbon dioxide from the atmosphere. Probably the simplest technology is you grow trees, you burn them, you do carbon capture, and you store the carbon underground. So if you think about that as a way of producing energy, it also sucks carbon dioxide out of the atmosphere. But it's expensive, so people don't do that. It's much cheaper just to not put it into the atmosphere. And estimates of the social cost of carbon, US government estimates it's about $40 a ton. So nowhere near the cost that would actually incentivize you to pull it out of the atmosphere. But, you know, technology improves over time. So it very well may be that it's cheap 50 years from now to suck carbon dioxide out of the atmosphere. And that's kind of one margin you might think about. Put it in today, but suck it out 50 years from now when it's cost effective, and maybe we know more about how dangerous it is. But maybe there's some risk associated with that strategy. So that's the kind of thing you might want to think about. So our XT goes from 0 to really an unlimited, it could be greater than 1. Whatever you don't mitigate goes into the atmosphere as emissions. It increases the amount of greenhouse gas levels, which increases the radiative forcing of the Earth, the amount of heat, and that leads to damages and lower consumption in the future. So one of the parts of the model that is very uncertain is how this all works. But you can certainly build in that uncertainty, which is what we do. Let's see. But before I say that, let's also say it is costly to mitigate. And so we have to specify something about the cost function. And we're going to look at, you know, a standard cost function that actually does allow us to, at some level, you know, suck carbon dioxide out of the atmosphere at basically an unlimited scale. So there's a maximum cost. When you start doing that, we assume, and then we also assume that there's technological change that will reduce those costs over time. So the agent chooses a level of mitigation today, an XT. And by the way, we're operating in a representative agent environment. So there's just one decision maker representing all of society. He or she is infinitely live. And the question is, what's the optimal utility in terms of consumption and mitigation?
So the choice variable, the choice object, is it a whole path or is it a single number?
It's a whole path.
Whole path, okay.
Yeah. And now, on the other hand, let's say consumption before damages is exogenous in this model. So that's definitely a limitation of the model. We're not taking into account growth uncertainty. And we're going to assume a fixed growth rate, like 1.5% a year or something, or 2%. We do a lot of sensitivity analysis to these parameters, but that growth rate is taken as given, and then what affects it are the spending on mitigation and the damages, which both subtract from the maximum consumption that would otherwise be available. So the uncertainty in our model is the relationship between those greenhouse gas levels and damages, and we're going to create that mapping by doing a bunch of simulations. And we characterize that uncertainty in terms of this latent variable theta, which I think of as the fragility of the environment. So we don't know theta, we learn about it over time, and for a given amount of greenhouse gases, it's really the whole path of greenhouse gases. We have an amount of forcing, which leads to an amount of damage. And we learn about that and then experience it over time. So we have a degree of, so our utility function is Epstein's in, which allows us to separate out intertemporal substitution, which is, how much we would prefer consumption today to consumption in the future, versus risk aversion, which is how much do we prefer consumption in good states of nature versus bad states of nature. And that we separate those out using Epstein's in because financial economists decades ago realized that if you just think about a standard power utility function, which specifies a degree of curvature, the amount of curvature that's required in order to generate risk aversion that is consistent with the equity market, which reflects a very risk-averse society, is much too much curvature to be consistent with the low real interest rates that we see of, say, 3 or 4%, or 2 or 3%, whatever. The curvature associated with a high equity risk premium would lead to real interest rates of maybe 20%. Now, you might wonder, why is that? And it has to do with the fact that, basically we assume that consumption is going to grow over time. So you can think of people in the future as being better off than people today. Consumption today would be much more valuable than it will be in the future when everyone has more consumption, and therefore it requires a pretty high real interest rate in order to induce me not to consume today, but rather to save.
Yeah, there might be another effect which is well known in interest rate model theory. The discount factor is convex to the level of the rate, exactly as it's convex to the maturity. So any uncertainty either on the maturity and the level of the rate would reduce the expectation of the rate. Yes, it does.
It does, absolutely. And you could say that is taken into account, but it's not a big effect in this model, but yes. So the importance of risk. Well, so when I first started reading this literature on what are called integrated assessment models, and you can see an example in this graph. What you see here, I'll have to tell you because you probably can't read it, but it says income elasticity of marginal utility on the horizontal axis, which is basically the degree of curvature. And so in this graph, for whatever reason, they have it increasing as you move from right to left. So I don't know if this is I don't think that's a laser, but as it's coming toward me and those lines are going down, it's a more risk-averse utility function. And what those lines represent, the vertical axis is the appropriate price of emissions, dollars per ton of carbon. And so what happens in these standard models is, as the utility function becomes more curved, and these models are not using Epstein's in, they're using power utility. So as the utility function becomes more curved, what that does is it raises the real interest rate, and that higher real interest rate means those damages in the distant future are less valuable today, and so the appropriate price goes down. Well, if you're thinking about what's the impact of risk on the price of emissions, you find this kind of counterintuitive. You basically say, if I want a high price, I have to make my individual less risk averse. Okay, kind of goes the wrong way. And so that's why we decided, maybe we should use Epstein-Zinn and see what happens when we do that and separate out these impacts of risk from, intertemporal substitution. Now, this is just an illustration of the equity risk premium. And what you see here is, long-term bond returns. I haven't updated this in a few years, and long-term cumulative returns on equities. This is on a log scale. Data comes from the Schiller database. And if we fit lines to these different curves on the log scale, it's basically the long-term returns from these two different asset classes. And that difference between the real bond return and the real stock return is about 4.75% per year. Very high difference. And as discussed earlier, that's explained by the amount of risk aversion in society. And economists have called this the equity risk premium puzzle, because the puzzle is, why is it so large? Why are people so averse to this risk that, looks like over a 30-year period, it's very unlikely that you're going to underperform bonds. You're likely to outperform by a very significant amount. And why is it such a high amount? Well, we don't really have a good answer. But what we can do is we can certainly calibrate to it. So that's the basic idea here, is let's calibrate the social cost of carbon to economic variables that we observe, such as the real interest rate and the degree of risk aversion in society as reflected in the equity markets. And so here we illustrate what happens if you start with a equally volatile portfolio, one of which is long equities and the other of which is short equities, along with bonds. And what you can see is, basically that outperformance of equities over bonds in the long run is also reflected equally if you're short equities and long bonds. And so you have a negative return to that short portfolio. And the important idea here is that if you have an insurance-like payout, you're going to get less than the risk-free rate. Now, that's important because, years ago, before economists really understood how this applies to climate risk, they used to say things like, well, an investment in mitigation is risky, so it should get an equity-like return. Or they would say, well, we can invest in mitigation, or we can invest in real capital that'll provide an equity-like return, so it requires an equity-like return. 7% a year or 4% real or whatever. And they would discount all of those cash flows by that risky rate. Of course, that's not the way we do things in finance. We look at the marginal utility in the states of nature where cash flows occur, and we price them appropriately. There's a question in the back.
Yeah, I was just wondering, about how we consider all scenarios to be very serious ones.
Right.
And typically, when we're pricing risk in a financial portfolio, we know what the downside risk is. But it's $100 you started with, so that's your the amount. Whereas here, it seems the potential risk is, infinite. We could just not be able to live on that.
Well, as financial economists, we know how to price futures or whatever, and they have unlimited down. There's plenty of securities that have unlimited downside. If you go short equities, you have unlimited downside. So it's not that, but there certainly is a lot. There are a lot of issues that are raised, and we don't. If you said to me, which interest rate are you looking at? Well, I don't know. Is it because we don't see a real rate 200 years from now, right?
I guess related question would be, we could, I forget what that's called. You know how I could price a risk preference for a payout 2 years from now and a year from now, and figure out what my preference is. But then if I ask you what that preference is from year 29 to year 30, I might be indifferent.
Yeah, but I don't really care what your preference is, because I can see what the interest rates are and therefore I can tell you, here's what it'll cost you to, create a contract that you'll pay $1 a year from now and get whatever. Yeah.
And your target risk premium can change in 29 and 30 years. You may be inclined to make choices in the future that you would never agree to once the future is tomorrow.
Well, the question is, where do you price that? First of all, if you're talking about the, real bonds, the whole idea is that these things pay out in all states of nature, so they're not risky. But of course, they will change in price between today and tomorrow because there might be shocks to the economy. And that's true. You'll see in this model, it's a dynamic model. We'll get new information, prices will change over time, and we'll react to that. That's actually an important feature of this model. A lot of these integrated assessment models just they assume we're going to price emissions at, let's say, $40 today, and it'll go up at 2% a year forever. Okay, and then they consider that versus starting at $35 or $50 going up 2% a year forever. That's not how the real world works. You make a decision today, you set a price, and then next year you have new information, you set a new price. You don't pre-specify. So yes, it's really an optimal control problem, and we want to take that into account. Now, wow. I'm going to have to run through this very quickly. I barely got into it, and I apologize for that. But so we're using Epstein-Zinn. Epstein-Zinn makes a big difference. You saw that earlier graph that looked a little bit like this light line that came down as we increased risk aversion. This is what happens in Epstein-Zinn utility function. We increase risk aversion, holding fixed interest rates, and what you get is a higher price for carbon. So that's the first thing that we're trying to get out of this model, and we do get it. We won't talk about that. This is a very simple model. Their markets are complete. There's no transactions costs. We're not taking into account heterogeneity. We're basically asking in this representative agent model, where all information is known, by the way, the agent knows what all the potential outcomes are and how do you take it into account. So this just says that the consumption in a particular period is going to be that endowment consumption minus the damages and minus the costs of mitigation at that point in time. And the damages are a function of the amount of mitigation. This is the whole path, and the degree of fragility in the economy, theta t, which gets revealed over time.
Is there a distinction between capital X and little x?
Yes, little x is the mitigation today at time t, and capital X is the whole path of mitigation that determines damages today. Mm-hmm. So that's pretty clear. So in our representative agent setting, the agent internalizes the consumption damages and sets mitigation each period so as to maximize lifetime utility. So basically, we're doing an optimization over all of the XTs. And we solve for the socially optimal. We maximize the utility function. And basically, having solved for the XTs, we can then back into the price that would generate that amount of mitigation. Okay, our cost curve is estimated from, this is something that's called the McKinsey cost curve, and it kind of tells you, we ignore this part of the curve. It says there's all kinds of negative costs associated with mitigation, like replacing incandescent light bulbs with, LEDs. But we do look pretty, we kind of use that part of the cost curve. We just assume that it's a positive cost to reduce emissions, and we fit to this curve. So it looks something like this. So today it's pretty cheap to mitigate at first, but you get up to 50% mitigation, it's going to cost a significant fraction of consumption, and to get to 100% mitigation today, much more significant, and so on. And then at some point it kind of flattens out, and we can just mitigate at a constant cost, and that's why it becomes linear there. So then you've got a backstop. So this looks at the marginal cost of mitigation, and you can see, you know, at whatever, $40 a ton, you'll mitigate something like 40%. As you get to $400 a ton in our base case, you know, you have unlimited mitigation at that point. So we do allow technological change. Let's just say that we allow for two kinds, endogenous and exogenous. The endogenous is just that, you know, the cost decreases at, say, a constant 1% a year. The endogenous says the more you've mitigated, the more you learn about mitigation, and it reduces the cost even more. So we just explored a little bit what those things do. There is a lot of uncertainty about damages. This is just something that comes from climate science, you know, and kind of shows that there's a pretty significant uncertainty about what a given level of mitigation will do to temperature. We kind of take that into account, and we estimate this damage function. Boy, I could spend a lot of time talking about how we do it. Let me just summarize by saying we tried to create a model in which there were kind of tipping points and low probability but catastrophic events, and we parameterized those things. We did not actually try to take climate science to tell us what those parameters were. We just looked at sensitivity to it. It turned out at the end of the day, we didn't really create a lot of risk. We have a decomposition of the social cost of carbon into the component that comes from expected damages and the component that comes from a risk premium, the curvature of the utility function. And because we basically have enough time and resources, and we see that, you know, if we happen to get a bad draw, we can mitigate. We can prevent that from really having, we do a lot of mitigation. You know, those bad draws occur typically 200 years from now, and instead of having a lot of heating in the atmosphere, we say, as we learn that we might be in a bad state of nature, we're going to do more and more mitigation. And so we do certainly get damages, and we spend a lot of money to mitigate, but it's not risk. It's expected damages in the context of the model. So I could talk about how we tried to put these catastrophic outcomes in, but at the end of the day, I would say there's not a lot. It didn't really affect it. So let me just quickly kind of go through that. And ultimately, what we do is a bunch of simulations based on temperatures and based on different parameters here. This is a key parameter. We introduced these tipping points, and we said as temperature goes up, the probability of the tipping point increases. And we just parameterize at what temperature we hit 100% probability. It could be as low as 5 degrees change, or as high as, you know, 17 or more. So that's one of the parameters that we played with. Another parameter was, suppose we hit one of these tipping points, what is the amount of damage? And so we have, you know, various different functions that represent the probability of, you know, being out here or out here, and we can parameterize the damage conditional on a tipping point, and that's how we get different damage distributions. And then we build in 6 periods. So we have today, which is 2015, and 2030, 2060, 2100, 2200, 2300, 2400. And we look at the temperature at each of these points. Each of those points is a decision point where we can choose to mitigate a different amount. And this has a tree structure a lot like pricing options. So today, we don't know what the beta is. In 2030, we learn that we're either in the upper half of the distribution or the lower half. Actually, not. It's a recombining tree. So we've gone up, down, and then from 2030 to 2060, again we go up or down. So we learn which of those possible states. In other words, let's say we go up from 2015 to 2030. Up in our model is a worse potential outcome. Well, well, we've just eliminated the lowest possible outcome in the tree. Or if we go down, we've eliminated the worst possible outcome of the tree. And there's only 6 potential outcomes in 2,400. So because it's a recombining tree. However, like with mortgages, this is path dependent, because if let's say I go up, down, I've done a different amount of mitigation than if I go down, up. So that so we have to keep track of that. And okay, this is kind of the bottom line on those simulations. So we simulate with different pathways, like a 450 pathway, which basically means an amount of greenhouse gas emissions that leads to ultimately 450 parts per million. So that's a lot of mitigation. Or business as usual, it's sometimes called, kind of no mitigation, leads to kind of steady state of 1,000 parts per million. And obviously, you get a lot more damages at 1,000. And so what you see here is kind of the different states of nature. You get a bad state of nature, you get very high damages with 1,000 ppm. You get a bad state of nature, but you only have 450 ppm pathway, much lower damages. So you kind of go through time. You know what this is at the beginning, but you don't know which state you're in. So over time, you learn what the probabilities of different states are, and you react differently depending on whether you're in a good state or a bad state, which finally gets revealed in 2,400. Now, we do those simulations, and then we interpolate so that if we're in, say, let's see, this is average emit, right? So you can think of a continuous amount of mitigation, so you're not exactly at 450, you're not at 1,000, you're somewhere in between, and then we interpolate from those simulations to give us a continuous mapping. So for any given degree of mitigation, we can estimate what the damages are going to be, and this will be true for any state or and greenhouse gas pathway. And this is kind of what our model looks like as a tree structure, and there's different pathways. This particular node. So if you're in a node, you're now making a decision: how much should I mitigate in that node? There's mitigation decisions at each node, and then at this final point, and then we allow the consumption to grow continuously from that point forward with a fixed amount of damages, whatever the damages in the state are. Consumption grows from there. As I said, increasing fragility, more damages going up in the tree. So you can imagine if you get to this point, the blue pathway, you've already done a certain amount of mitigation. Because you thought you were in a bad state here, you did more mitigation. When you moved down here, you said, things aren't so bad, I won't mitigate as much. But then over time, you found that no, things are worse. And so, you can kind of see how you move through this. And it's a lot like an option pricing tree. And we just solve this model numerically for the different potential mitigations at all those different nodes. And that gives us a utility. And we optimize over that. Unfortunately, by the way, it's not a convex function. So, you can imagine there's some numerical issues that have come up. You might think of a pathway where I mitigate more here and less there, or less here and more there. And you can jump, depending on parameters, you can see that, gee, rather than following that strong mitigation, the optimal policy is now less strong, but more strong later. So different strategies to search over.
Sigmoid that you showed, that's why you have this complexity.
Well, I think you think because of the cost function and the potential for, well, that's certainly one part of it, but I'm not sure if that's the only thing. So this is where we write down, and I won't go through Epstein's in, but it's obviously a more complicated utility function. Although if you're, what are the parameters? Alpha and rho are the same. It boils down to power utility, but the alpha and the rho here allow you to specify different degrees of risk aversion and intertemporal substitution. So our base parameter cases are beta, which is basically pure time preference, 0.995, which means an interest rate of like 50 basis points a year. And that's how much we prefer utilities today to utilities tomorrow. It's not an interest rate. But then the degree of intertemporal substitution is that's rho, and that we use to match a real interest rate of 2.5% a year. Actually, we changed that in this version of the model with 2.1. We just lowered it a little bit, and risk aversion is 7. For those of you who are familiar, it takes a risk aversion greater than 7, significantly greater, to price equities, but we reduce that a little bit because it's hard to explain why society is that risk averse. And then we get various different paths for the social cost of carbon. Now, in practice, in this tree, there's multiple prices at every point except today. So today, we know what the price is because there's one node. Next period, there's going to be 2 nodes. So what we're showing on this graph is the expected price. If you're in the up node, it'll be a higher price. If you're in the bottom node, a lower price. We give the tree 50-50 probabilities of moving up or down. And so these are the expected prices over time. And you can see they do go up at first, but then they come down. They come down primarily because of that technological change. Makes it cheaper to mitigate. These are a couple of different cases. Again, I want to kind of go through it quickly. So our calibration yields an initial price of $40 here, and then you can kind of see how the prices of these different nodes are developed, associated with different degrees of mitigation. Yeah, the optimal level of future mitigation is higher if you find out that the world is going to be more fragile, etc., just what you would expect. We do use the backstop technology in almost all states after 2100. This is the amount of mitigation, and you can see starting here that price of $40 is 42%. But then up here, in all these where the mitigation is greater than 1, we're sucking carbon dioxide out of the atmosphere. And by 2300, only in the best state of nature do we not do that. Okay, consumption's lower in the high fragility state because damages are high, and also because you're mitigating more. The cost of mitigation is highest when good news is followed by bad news. So you sort of do it this way and then up. So this is a good example: down, down, up. You're going to do more mitigation, and the cost, which is here, like 2.4% of income with that. It's going to be more than you go up, up, down, down, for the same fragility, but you've done more mitigation, so you don't have to do as much. So that's the path dependency. We also look at some interesting things that other models are not able to address, such as early versus late resolution of uncertainty, endogenous versus exogenous change, different backstop technologies, different growth rates, different preferences, and cost of delay. That last one is kind of interesting because what we can ask in the context of this model is, what's the social cost of carbon, meaning we start today and price emissions. We can also ask, what if we don't start today? What if we wait until the next period, which in our model is 2030? So during the first 15-year period, we don't price emissions. Well, that roughly triples the social cost of emissions from $40 a ton to $112 a ton. And you can see we're kind of wasting capacity, and that's a dead weight loss. You can't make it up. If you ask how much is that dead weight loss, that is equivalent to destroying 6% of consumption throughout that whole period. So it's a very significant cost of delay. And, it's just crazy not to do it. We, by the way, this is what we call our base case, and the social cost of carbon is $40. That's not our result. I want to be clear. This is a toy model, and we just said, let's take these damage parameters and set them to match the U.S. government estimate. So we set our damage function such that we get $40 a ton, and then we do the question, what happens if we don't price emissions for 15 years? And it's really $112 a ton. And by the way, if it's $112 a ton, and right now we're producing something like 50 gigatons of pollution, so it's something like $5 trillion of damages, this dead weight loss per year. So it's a very significant cost, not pricing emissions. And then we also look at a high risk scenario. So suppose instead of calibrating to $40 a ton, because we don't really know what the social cost of carbon is, suppose we calibrate to $150 a ton. Well, then that constraint raises the cost to $450 a ton of damages. And just intuitively, we're using up whatever spare capacity there might be, and that's why that same ton is much more dangerous if we don't price emissions immediately. So, and in this case, certainly the equivalent cost to society is not 6% of consumption, but 36% of consumption. And I have no reason to think that I know that it's $40 a ton. In fact, there's reasons to think that that estimate by the U.S. government, which doesn't really take risk into account, might be much too low. All right, but I would also say again, I don't want to claim too much for this model. We have this nice risk decomposition, and in our model we don't find much risk because it's you know it's coming, and you're able to. First of all, the marginal utility of consumption in those bad states is not that much worse than in the good states because we don't have those damages are not that great. The worst damage we saw out there, this was with our base case, was like $40 a ton. Go back to that, not $40 a ton. It's actually 65%. If you get the worst case and you've done no mitigation, you get 65% damages. But you don't not mitigate. You do mitigate, so you're not getting 65%. You're getting, in this case, this is a 450 pathway. You're getting 35% damages. But also remember that's in 2400, and your baseline consumption is growing at whatever 2% a year. You've got 5 times or more, actually more than 5 times the amount of consumption that we have today. And the worst case, you're kind of losing 30% of that. But the marginal utility between here and there, it's not that big, and that's why the curvature doesn't really have a big impact on the price. Now, having said that, I don't take that as actually a finding. That's just in our model. And I would say what you really need to capture, call it risk in this model, is the possibility that you get a catastrophic outcome here that you didn't expect. But we don't have that in our model, even though we kind of tried to build it in. We realized perhaps too late that actually there's no risk. But as a society, there's clearly risk. Clearly, this model is misspecified, etc. We don't know that this model is right. We don't really know a lot of what those damages look like. And so I would say we have to be very cautious, which raises the price. I think the irony here is these folks who've been denying climate risks for so long act as if the uncertainty about it means we shouldn't do anything. The uncertainty in this broader sense means we should be at the high end of the uncertain social cost of carbon. Happy to take questions.
Yeah, I'm just talking about the uncertainty. Even if you assume that the data is $40 is an average, obviously if you go down to, it can be anything between 20 and 80. Even if your 150 is very high, let's assume that there is a range.
The IPCC in its last report said, you know, with these models, you can get anywhere from $2 a ton to $200 a ton.
Okay, so the standard
very
is
wide.
very big.
Yeah.
And now you have, you know, through the complexity of the output, the expectation of the output is way higher than the value that you could get for precisely $40. That's basically
That's the risk aversion, yeah.
So the impact, I mean, the expected impact should take into account that complexity.
Yeah.
Fragility.
Yeah, it's just, as I say, in this model where you kind of know everything in advance and you have enough time and it's not that expensive, you can address it down the road if you need to, kind of thing. So turns out in this model, the risk today is not driving it, it's the expected damages. Yeah.
Other than this number, $40, is there anything specific to climate here? Would not the same apply to anything where you think there is some damage now and which can be mitigated, like bed consumption?
Yeah, you could use the same basic structure for any action that you take that causes damages in the future, that has an externality. What is special about climate, or not necessarily special, it might be like creating radioactive pollution or something. It's long-lived, and so those damages may occur, you know, significantly out in the future. Very uncertain what those damages are. So anywhere where you have that long-lived uncertainty and potential damages, particularly catastrophic outcomes, yeah, you want to buy an insurance policy, more or less. So of course, yes.
So nothing specific to climate, apart from this number $40, which is very debated.
Well, the $40
Maybe
is
minus $40.
the $40 is calibrated from a damage function that, in theory, we could get from science. Okay, we don't know. Well, let's put it this way: the only reason we're doing this is because scientists tell us that there's a lot of uncertainty about the outcomes. In other words, they're saying there's damages out there. Some people have made the point that, you know, shouldn't we be worrying about, I don't know, meteorites or you know, asteroids hitting the Earth? And shouldn't we be worrying about nuclear war? And shouldn't we be worrying about, I don't know, biological weapons that might get out of control? And, you know, my answer is, yeah, of course we should. So if you're saying, are there low probability, potentially catastrophic outcomes other than climate? Of course, many of them. And should we worry about them? Yeah. I'd sometimes say, you know, what about, you know, nuclear war? That's a good one. That's pretty legitimate concern. Should we think about it the same way? I guess the answer is yes, but one difference, and to me this is a very significant difference, is I assume, perhaps falsely, that governments are concerned and are in effect spending appropriate amounts to protect us from the potential of nuclear war. Climate risk, I can observe what's being spent. The answer is nothing. So, you know, that can't be right. So that's kind of the difference. But yes, we should adequately insure society against any potential damages and dangers that we know about. Yeah.
The fact that maybe the risks are not distributed evenly. So, for example, the coasts of continents are at probably bigger risks than the middle, and I don't know. You might even wonder whether that doesn't drive part of the politics. Who cares the most about?
Oh yeah, I'm not trying to address the politics so much here, and you're right. The heterogeneity is important.
But Miami, for example, I would say is very concerned, but for East and California and East Coast, well, maybe in some sense the middle of America would feel a lot safer.
Yeah. Yeah. Oh yeah.
Maybe welcome the warm weather.
Canada might like this. You know, makes it warmer. Russia might like it. Yeah. So
I wonder whether the price might be related to trading across countries, but I don't know if there's some work in that.
It could, you could make this model much richer along those lines, but it also obviously much more complicated. So this is trying to just focus on the really the intertemporal issues associated with how much, if we're all equally wealthy, so to speak. That's another one. People worry a lot about climate risk can be mitigated or adapted to is actually the right way to say it, much easier in a wealthy country. Whereas in a rural, poor country, it's hard to adapt to climate risk. Of course, we're all going to be very wealthy out here somewhere. So I think that's kind of, that's a complexity we haven't taken into account. Yeah.
I don't know much at all about cap and trade, but I'm just curious. The concept there basically say, well, once the society charges producers actual money, right, then I guess the argument is that once you're able to transfer that cost or have somebody, I guess you don't know how much you have to pay for ultimately for the damage, but you could basically have somebody price it for you, some other agent in the market. Am I thinking of it correctly? The cap and trade?
I know where your confusion is coming from. A lot of people are confused. They think somehow if we put a cap on this, the market can determine the price for you. The problem is, number one, we don't know what the cap is. That's kind of like, okay, do we know what the capacity of the atmosphere is? No, it's uncertain. So there's so a cap kind of assumes away the uncertainty. And then the other thing that happens with a cap is, so in Europe, they have this trading system with a cap, and then they have a recession. And so there's not as much pollution being created. So the price drops. Yeah. The social cost of carbon hasn't changed if you think about a 200-year time horizon. But I don't get too excited about the difference between a cap and trade system or a tax as a way to create this incentive, because you could structure either of them to create the incentive that you want, the appropriate price. So if I have a model that tells me the appropriate price is $40 a ton, I could devise a cap and trade system that would make sure I get there by building in appropriate flexibility. So I can either issue more permits or pull them off the market if I'm the government setting up this cap and trade system, or if I want to just create a tax, I can just set it where I want. Now, a tax is not necessarily better if it becomes more rigid. In this country, we set gasoline taxes and then we can't change them for 20 years because, so what's important, and what I argue is important, is that we adjust the incentive appropriately across time as we get new information. If it needs to go up, we move it up. If it can go down, we move it down.